Hello and welcome to Mini Lecture 30 on solving ODEs, the last mini lecture of this course. Alright, so we've talked a lot about ODEs so far in this class. We talked about how to derive them, how to guess and check their solutions, and how to find the equilibria of these ODEs. Alright, so as a reminder, we can derive an ODE from diagrams such as a flow diagram as one way of deriving an ODE. So here we have the derivative, d by dt, of our state variable f is equal to the flow in minus the flow out, which is g f of t minus r f of t, or simplifying this, we get g minus r times f of t. All right, now to get the rest of the initial value problem, we also have to include the initial condition where at time 0, the state variable f is equal to 1. All right, so far you've learned that how to solve an IVP is that you guess the solution, and so far we've only tried to guess simple solutions such as an exponential function or a line, so we can guess some solution and then we can check that solution. So let's suppose we guessed this function here. If we take the derivative, we have d by dt of f of t, which is equal to d by dt of e to the g minus r times t. Taking the derivative, we have the derivative of an exponential, which is just simply the exponential. But then we have to use the chain rule. So we have this as our u, and we take the derivative of that, and we get g minus r, or simplifying, we have g minus r times e to the g minus r times t. And this indeed is equal to our function over here. All right, so note that this here is f of t. So we have g minus r f of t. All right, so that one works out. We also have to check the initial condition. We plug in f at time 0, and this should come out to being equal to 1. Plugging 0 in here, we have e to the g minus r times 0, and anything to the 0th is 1. So that indeed checks out, and we have the initial condition. So it's great to be able to guess the solutions to differential equations and to check their solutions. Checking something is always a good step in math, but it's kind of unfortunate because what if we don't know how to guess the right answer? What if they have something more complicated or aren't 100% sure what to put in the exponent? All right, well, it turns out that now that you know how to integrate, you have another tool in your toolkit for solving differential equations. And that is what we're going to use today. And the method that we're going to use is called separation of variables. And this is a very apt name because we're going to end up separating the variables in our differential equation. So let's start with our differential equation. We have df of t dt is equal to g minus r times f of t. And we note that this here is our state variable. This here is our state variable. And here we have our independent variable. And what we're going to try to do is we're going to try to put our state variable on one side of the equation and our independent variable on the other side of the equation. The key here is we can treat the numerator of this fraction and the denominator of this differential operator as separate objects. So remember that we can write a differential operator in fractional notation, and when we do so, we can separate the numerator of that fraction from the denominator of that fraction. So what we end up with is d f of t is equal to g minus r. Now I'm going to take this f of t here and I'm going to move it over to the other side of the equation by dividing both sides by f of t. And I'm going to multiply both sides of the equation by dt to move the dt over to the right-hand side. So we have this. All right, well, that might look a little bit confusing, but the cool part is that now we can integrate both sides of this equation. So we're going to throw an integral there and an integral there. I'm just going to rewrite this. We have the integral of 1 over f of t df of t is equal to the integral of g minus r dt. Now, we just do some integration. We know how to integrate 1 over x dx. That is equal to the natural log of x. So simply, we have the natural log of f of t. Now, don't forget your integration constant. We're going to put a little integration constant c1 there. All right, similarly, we have the integral over here. This is simply an integral of a constant. This has a little t to the 0th in it. We're going to use the inverse power rule to get g minus r times t. Now, don't forget your integration constant. We have a c2. The cool part is that this integration constant here and this integration constant here are both unknown constants, and so we can combine them into one. There's no reason to have two unknown constants in our equation. So we end up with ln of f of t is equal to g minus r t plus c. C is equal to c2 minus c1. All right, so that's all good. Now, the third step is that we're going to try to solve this equation for our state variable. Sorry, this should say state variable. All right, so we're going to solve both sides of the equation for the state variable. So just to rewrite it so that we're on the same page, we have g minus r times t plus c. Now, how do we solve for this f of t? You know how to solve logarithm functions. You're going to end up taking an e to both sides. You have an e to this side and an e to this side. Note that this whole thing is in the exponent. All right, if you take the e of the natural log, those just cancel, and you just end up with f of t. And then if we have this here, we have e to the g minus r times t. If you have a sum and an exponent, another way of writing that is as a product. So you have e to the c. Now, this is an unknown constant. E to an unknown constant is some number. It's still an unknown number, so we're just going to call that a new unknown constant. You see a little theme here that unknown constants are kind of convenient because they often lead to other unknown constants and can just be replaced by other unknown constants. So, we have some unknown constant c prime, e to the g minus r times t. All right, now we're almost done. We have our function is equal to something over here, but what is c prime? We still don't know what that constant is, so that what we're going to do to solve for that constant is we're going to plug in the initial condition. So we know that f of 0, according to our initial condition, is equal to 1. Plugging that into the right-hand side of our equation, we have c prime is equal to g minus r times 0. Anything to the 0th is 1, which means that c prime equals 1. Plugging that into our equation up here, we have f of t is equal to 1 e to the g minus r times t. And this is our solution that did not involve any guessing whatsoever. Just to go over those steps one more time, the first thing we're going to do is we're going to separate our variables, putting the state variable on one side of the equation and the independent variable on the other, where you can treat this fractional representation of a derivative as a separate numerator and denominator. Then we integrate both sides. Then we solve for the state variable. And then finally, we plug in the initial condition to obtain this unknown constant. All right, so give those 4 steps a try by using them to solve the following initial value problem.